Hi, this is Dr. John Bergduff. For some time now, we've been talking about functions and different properties of functions and different types of functions and graphs of functions and many things about functions, probably more than you really wanted to know. Today, we're going to talk about a special category of functions called one-to-one functions. Now, to understand this, which is actually going to turn out to be a very simple concept, we're going to need to go way back to the first principles of what we originally said a function meant, and from there it'll be easy to draw a distinction with one-to-one functions. So going way back to probably the first lesson you ever saw in functions, a function is first of all a relation. Now, a relation is simply a set of ordered pairs defined in some way. A function is a relation in which no two different ordered pairs have the same first coordinate. Now, that's a function. What's a one-to-one function? Well, first of all, a one-to-one function is a function. So you have to start with a function in which no two different ordered pairs have the same second coordinate. So in addition to no two different ordered pairs having the same first coordinate, no two different ordered pairs can have the same second coordinate. So let's look at some examples. These are some relations, sets of ordered pairs. We're going to first of all ask the question, are they functions? And then second of all, are they one-to-one functions? So let's look at number one, first of all. To be a function, no two different ordered pairs can have the same first coordinate. If I look at all of my first coordinates, I notice that they are all different, so this will classify as a function. Is it a one-to-one function? Well, to be a one-to-one function, no two different ordered pairs can have the same second coordinate. And if you look really carefully, this ordered pair and this ordered pair have the same second coordinate. So although this is a function, it is not a one-to-one function. Okay? Let's look at the second one. The second one is a reminder that the elements in the ordered pairs need not be numbers. Often they are, but they don't have to be. First of all, to be a function, no two different ordered pairs can have the same first coordinate. All these first coordinates are different, so it is a function. And to be a one-to-one function, no two different ordered pairs can have the same second coordinate. Excuse me. And if you look at all of those, they are also all different. There's no repeats there either. So this is, in fact, a one-to-one function. So that's one of those new categories of functions that we want to look at. All right, let's look at number three. So in number three, we ask ourselves, first of all, is this a function? No two different ordered pairs can have the same first coordinate, but if you look at this, you will notice that all the first coordinates are, in fact, the same. So this, in fact, is not a function. And then there's a slight trick on the second one, just trying to trip you up a little bit. When you look at the second coordinates, no two ordered pairs have the same second coordinate. All these second coordinates are different. And so it might be tempting to say, oh good, it's one-to-one. But if you look again carefully at the definition, a one-to-one function must first of all be a function. So it's a special category of functions. If a set of ordered pairs is not a function, then it can't even be considered as a one-to-one function. So this is also not a one-to-one function. You actually could be quite fine to define something more general called just a one-to-one relation, where you don't care whether it's a function or not. Just are all the different does each ordered pair have a different second coordinate? That would be a one-to-one relation. Now we're not going to use that term, but it certainly would be quite valid. Now, relations, i.e. sets of ordered pairs, are not always written as ordered pairs, like in those very first few simple examples. We see relations in many other types of formats. One of them would be a table, and if you've looked at my videos, you may recognize this one. This table, which might be something you might see on the Weather Channel or in a newspaper, shows in one column the name of one of the 6 largest cities in the U.S., and in the right-hand column what the high temperature was on July 17th of 2020. Now, although these are not written as ordered pairs, they really are ordered pairs. There's a first coordinate connected to a second coordinate. For example, New York City is paired with 84 degrees, and so forth. Is the following relation a function? No 2 ordered pairs have the same first coordinate? That's right. All of these first coordinates are different, so this is a function. Is it a one-to-one function? Again, in a one-to-one function, no 2 different ordered pairs can have the same second coordinate. And if you look right here, it just happened to be the case that the high temperature in both Chicago and Philadelphia on this date were both 89 degrees. That would be the same second coordinate in those different ordered pairs. So this is not a one-to-one function. If one of those cities had been a degree warmer or cooler, it would have been 1-to-1. Here's a different way to represent a relation as a mapping, where the first circle represents the values of your first coordinate or your domain, and the second circle represents the values of your y-coordinates or your range, and the arrows show which is paired to which. So, for example, we would make a pairing between Javier, a person, perhaps this is a group of 4 friends, and my domain is the set of the 4 friends, and what that's paired to is their height. So Javier is 5 foot 10 inches tall, and that would be the ordered pair that's represented by that arrow. Is the relation a function? I'm going to pause for just a second to see what you think, and then I'll say what I think. Is this relation a function? So I'm going to say it is a function. No 2 different ordered pairs have the same first coordinate. What would it look like if they did have the same first coordinate? Well, you would have to have an arrow maybe like this one. 2 arrows coming out of the same element from the domain, like from Marcus to 5'7". But what would that mean? That would mean that Marcus is both 6 foot 1 inches tall and 5'7" inches tall, and that doesn't make any sense. No one person has 2 different heights. So we can safely say, I believe, that this is indeed a function. Yes. Is it a one-to-one function? Do any of these ordered pairs have the same second coordinate? Well, these 2 arrows that are both pointing in towards the 5 foot 10 inches tells me that Javier is 5 foot 10 inches, but so is George. And those 2 ordered pairs would have the same second coordinate. So no, this is not a one-to-one function. Hope that makes sense. Here's another mapping. What I am representing in this mapping is, in the domain, a list of 4 friends. They all happen to be men. And in the second circle, in the range, these are their girlfriends. And I want to know, and then the arrow shows who Javier is paired with, who Tan is paired with, and so forth. Is the following relation a function? I'm going to pause again and ask you to think. Is that a function? And hopefully you saw that the answer is yes, that it is indeed a function. If Javier had been paired with another person, that would not function at all. Is it a one-to-one function? And again, let me pause on this one. Do you believe that it is true that no two different ordered pairs have the same second coordinate? And I think this is true as well. So no person is paired with more than one person on the other side. That would also be a problem. This is a one-to-one function, yes. No two different ordered pairs have the same second coordinate. If we had, for example, maybe a third person down here, maybe Mike, and he was paired with Karen, we'd still have a function because there's no repeated values of the domain element, but this would not be a one-to-one function because Karen would be paired with both Marcus and Mike. And that would still, I think, be a problem. Most likely. Now, it is also true that relations and functions are defined by graphs. And let's take a look at this graph, which I'm just going to jump in and claim. I'm just going to say it's a relation. And I want to figure out if the graph is a one-to-one function. Well, what we've kind of already seen is that a one-to-one function is a subcategory of the collection of functions. So we first have to ask ourselves the question, is this a function? That means no two ordered pairs have the same first coordinate. The picture would show that. Are there any ordered pairs that would have the same first coordinate? If they had the same first coordinate, like say there was another ordered pair whose first coordinate was 0, it would have to be some point either vertically above or vertically below the point that's already shown, and there's no such point. So I believe we can safely say that yes, this is a function. But is it a one-to-one function? Which is really what we were interested in. No two ordered pairs can have the same second coordinate. I want to look at, for example, this point right here and this point right here. Now, I don't know precisely what the x values are. That doesn't really matter. But I want to notice that the y coordinates for both of those points is 4. Both ordered pairs have the second coordinate 4. So you have two ordered pairs with the same second coordinate, and that tells you that this is not a one-to-one function. In fact, that's not the only example. Anywhere you look on here where you have 2 points that are immediately side by side from one another with the same y value, they have the same second coordinate, and therefore that makes this not a one-to-one function. Here's another example, way up here maybe. These 2 points that are side by side, same y value, those have the same second coordinate, not a one-to-one function. Even if there was only one example, that would be enough to make it not a one-to-one function. All right. Be thinking about whether there's some cutesy little rule that we once talked about looking at a graph and telling whether something was a function or not, and see if you can maybe guess whether there's some similar rule for one-to-one functions. But let's get to that later. Let's look at another couple examples. Is this relation whose graph is shown a one-to-one function? So again, we have to ask ourselves the question, is it a function? And we have looked at this many times. Any ordered pairs with the same first coordinate? Nope, I don't think so. So therefore it is a function. Is it a one-to-one function? That means, are there any two different ordered pairs with the same second coordinate? And I think no matter where you look, let's say you pick right there, there's no other point with 4 as a second coordinate. There's no other point with 2 as a second coordinate. There's no other point with -2 as a second coordinate. Each ordered pair has a different second coordinate. So this is indeed a one-to-one function. And we'll come back and look at this again later. Is the relation whose graph is shown a one-to-one function? Okay, now this is meant to be slightly a trick question because at first glance you say, hey, none of these points have the same y-coordinate. These y-coordinates are all different. So yeah, it must be 1 to 1. All those y-coordinates are different. No other points with the same y-coordinate. But in order to be a 1-to-1 function, you have to first be a function. And for example, these 2 points have the same x-coordinate, the same first coordinate. Therefore, it's not even a function, and therefore we have to say that it is not a 1-to-1 function. Again, we could come up with the concept of a 1-to-1 relation where it doesn't first have to be a function, but we are talking specifically about 1-to-1 functions. Now, did you notice or did you remember a cute rule for determining whether something is a function and how that might inspire something for a one-to-one function? Well, I wonder if you remember the vertical line test. For a graph to represent a function, each vertical line drawn through the graph must hit no more than 1 point on the line. So if I go back in a few of these examples, if you remember the vertical line test, we would have immediately said that this graph does not represent a function because when I draw vertical lines through the graph, I hit more than 1 point. This one is a function because when I draw vertical lines through this graph, no matter where I draw them, well, that one wasn't very vertical, but use your imagination, you only hit 1 point. And I'm going to clear this out just for a second here. And this one, the first example we looked at, still a function. Actually, I'm going to clear out the things that are already there. This is a function because when you draw a vertical line, anywhere you draw it, you only hit 1 point. Now, remember that this one here was not a 1-to-1 function because, for example, these 2 points have the same second coordinate, and they are directly side by side from one another. And so if I can go back here, I want to introduce you to another wonderful property called the horizontal line test. For a graph of a function, so you start with a function, to represent a 1-to-1 function, each horizontal line drawn through the graph must hit no more than 1 point on the graph. So this is very similar to the vertical line test. You do the vertical line test first to determine if you have a function, and then you look at the horizontal line test. This one was not a function, so no point looking at that any further. This one was a function, and if you look at what happens whenever you draw a horizontal line through this graph, you only hit 1 point, and that verifies what we had already decided, that that was a 1-to-1 function. By way of contrast, this graph, and it does represent a function, is not a 1-to-1 function because when you draw horizontal lines through the graph, you often hit more than 1 point. Now, the fact that there is a horizontal line that you can draw that only hits 1 point right there does not, unfortunately, make up for the problem that already exists. We already identify horizontal lines that go through more than 1 point. And there's even horizontal lines that don't hit any points, but that doesn't matter either. We're already messed up. So, very, very easy to look at a graph and tell whether it is a function, first of all, and then whether it is a 1-to-1 function. Now, as you will remember, the most common way that you're going to see a function represented is by an equation. Are the functions defined below 1-to-1 functions? Now, the good news is we've already done a lot of graphing, and so I think we can answer these questions often very easily by just thinking about what the graph would look like. Notice that number 1, for example, the equation is in the form y equal mx plus b, and we might remember that that would represent a line. Now, this is not a vertical line or a horizontal line because it has a slope of 3. And if you think about a line, as long as it's not vertical or horizontal, it will pass both the vertical and the horizontal line tests. So we can safely say that this is a 1-to-1 function. Just thinking about the graph and the vertical and horizontal line tests. Do you recognize the graph of the second one? I'm going to give you half a second to think about that, just the general shape. Hopefully you'll recognize that as a parabola. And a parabola will not pass the horizontal line test. It is a function, but it's not going to be a 1-to-1 function. Now, not every function that I'm going to describe for you will be of a type whose graph you'll immediately recognize. This last one, number 3, I think fits into that category. It doesn't really fit into any of the standard forms of functions that we've looked at. That doesn't mean you can't figure out what is going on. And some of the other examples may even give you a hint. The thing that made our parabola, number 2, not a 1-to-1 function, I think more than anything else was this exponent of a 2. Because what happens is when you square a negative number or when you square a positive number, you get a positive number both times. The idea of a 1-to-1 function, again, is that you can't have two different ordered pairs with the same first coordinate. But if you think about what happens whenever you have a square, let's just pick a number just for the sake of a discussion. If I pick 4 to be x, or if I pick negative 4 to be x, either one, when I square those, I'm going to get the same positive number, in this case 16, and that will cause the y-coordinate to be the same. Now, this isn't the prettiest y-coordinate, but that's okay. So when I saw that x squared in the radicand, that immediately brought to mind that whether my x was positive or negative, the y value would be the same. I'd have the same y coordinate, the same second coordinate, and that means that it would not be 1-to-1. So even though I don't immediately recognize the graph, I can still sort of think about the ordered pairs and represent and recognize that this is not a 1-to-1 function. Okay, that's it for this lesson. The only question that might be lingering in your mind is why on earth did we bother to even define this very special category of function? And I will tell you the answer to that question in the next video.